So first of all, is this thing, okay. First of all, I thank whoever for the opportunity to speak here again. Right. All right. So I'm going to talk about this is the counting analysis. We're going to count periodic orbits of Anosov flows in 3 manifolds. Yes, so first of all, let me say that this is joint work with Thomas Barthelme from Penn State University. I guess everybody here knows what an Anosov flow is, but very briefly. So a flow in a closed free manifold is Anosov if there are 2-dimensional foliations, so stable and unstable foliations. Right, so that in a leaf of the stable foliation orbits forward asymptotic, and in the unstable foliation they are backwards asymptotic. And the local picture is this. So this is my orbit. This is local stable leaf, local unstable leaf. You're expecting the orbits to converge together in future time along the stable and diverge. So it's sort of like the saddle type picture. Okay? All right, so what are sort of examples? So the talk will be really in 3 manifolds, but Anosov flows are defined in any dimension where you have this foliations, whatever dimension, so that they are transverse, complementary, intersect exactly along the flow lines and have this exactly this behavior. Okay? So in dimension 3, and actually this works for any dimension, so the geodesic flow in M, which is the unit tangent bundle of S, as of Gaussian curvature less than 0. For a lot of people here in this audience, just think S is a hyperbolic surface. And I have the 3 manifold, which is the unit tangent bundle. So the geodesic flow is Anosov. As a matter of fact, this works for any manifold of any dimension of a negative curvature. Right, so second thing is the suspension of Anosov diffeomorphisms of the torus. Think, for example, a linear automorphism, which is hyperbolic, meaning the 2 eigenvalues are real. One is bigger than 1 in absolute value, one is smaller than 1. Make a suspension of that, and that's going to be Anosov. Then there's this operation, then surgery on flows, which was done by Goodman and extended by Fried. So you do then surgery, which is operation in 3 manifolds. Okay? So remove a solid torus neighborhood of a curve and glue back by a homeomorphism of the torus. Now for flows, I did that, for a curve near a closed orbit, meaning actually isotopic to the closed orbit, and you get this curve to be transverse to the stable and unstable foliation, then you can do that. Fried did a generalization of that, where he starts with that orbit, he blows up that periodic orbit. So now we have a manifold with boundary, which is a three-dimensional torus, blows back down according to the Sergio coordinates, and you have a flow there that could actually be what's called also pseudo-Anosov, where we allow certain singularities. The singularities would be along that orbit that you're doing the surgery. But a lot of times you still get Anosov flows, if it's like one-end surgery. The interest here is that there are examples, and actually lots of examples, of Anosov flows in closed hyperbolic three manifolds. And more recently, Foulon and Hasselblad said that there are contact Anosov flows. Meaning that the flows preserve a contact form, which implies a certain property which will be later on really important for us. And there are examples of contact Anosov flows in certain hyperbolic three manifolds. Okay? So Anosov flows are very common. Okay? So there is a general question so in dynamical systems is to count periodic orbits. So how many periodic orbits does Anosov flow? And because of this this hyperbolic behavior, which we have expansion and contraction, you cannot have too many. So you cannot have orbits which are very near each other all the time and are periodic. Okay? So there is at most countably many, but there are always infinitely many. And so then another question, which is really important, what is the rate of growth of orbits? So we want to count how many closed orbits of period less than t, and this generates a function of t. And I want to know how does this grow. And then the the first results by Bowen and Margulies. So the growth rate of f of t is exponential. Okay, so this is actually, there's infinitely many orbits, but they're actually, as a function of t, this grows exponentially in t. And the growth rate, meaning that the exponential coefficient, the growth rate is associated with the topological entropy of the flow. Okay. And actually, there are, in a lot of cases, there are much better estimates, not just the exponential with the topological entropy as the rate, but the asymptotics can be actually quite precise. Okay. All right. So in the 70s, this was also, I guess, in the 70s. Lunti and Thurston showed that if tau is a codimension 1 Anosov flow. So like I said, you can define this Anosov flow for higher dimensional manifolds, and you're going to have the stable and unstable foliations. Codimension 1 means either the stable or the unstable is codimension 1 foliation, okay? Which is always true when you're in dimension 3. So this implies that the fundamental group has exponential growth. Okay. Now it turns out that codimension 1 is extremely important. As a matter of fact, there's a conjecture for higher codimension Anosov flows, which I'm not going to get into here. And they asked a question which generated this. So I'm going to state it for 3 manifolds, but you have the same question for any codimension 1 Anosov flow. So I know that if you have a codimension 1 Anosov flow, the fundamental group grows exponentially. So given a in M3, does the number of conjugacy classes in pi1 of m grow exponentially with the length of the shortest orbit representative in that class. Okay. So what does this mean? So we know that the number of orbits of period less than t grows exponentially. But now I'm going to identify orbits which are in the same conjugacy class of pi1 of m. So 2 orbits are sort of in the same conjugacy class if and only if they are freely homotopic. Okay. So now I'm going to bunch the orbits which are freely homotopic. So this is really a question now in the conjugacy classes of the fundamental group. So the more freely homotopic orbits there are, the less the growth in question 2. Okay. So some basic examples. So first, for suspensions, no 2 orbits are fully homotopic. So each free homotopy class has at most 1 element, and therefore when you're counting orbits, you're counting conjugacy classes. Okay? So then we already know that the number of orbits grows exponentially with the length of the shortest orbit. So the answer is yes. Okay. So then what about geodesic flows? So here we start seeing some freely homotopic orbits. I'm going to use the geodesic flows a few times in this talk. And I'll keep going back between the surface and the three manifold. As a matter of fact, a lot of times I'll just do stuff in the surface and refer to some fact about the geodesic flow in the three manifold. Okay? So now here in the geodesic flow, every closed orbit is freely homotopic to another orbit, and there's only one other. And it's very simple to see. So you take let's do it for sort of the case. So a periodic orbit here means the closed geodesic. This is an M. This is closed geodesic in S. Okay. So here's a closed geodesic, and an orbit means that I'm just picking a direction here. Okay. So if this is alpha geodesic corresponding to orbit, so the orbit corresponds to the points of the unit tangent bundle here. Right. So let's suppose that this closed geodesic is orientation preserving. So I can do what I'm going to do now. So I'm going to rotate these vectors by pi. And I'm going to get another closed orbit, which is the same geodesic but being traversed in the other direction. Okay? So there's two orbits in the free homotopic class, but there's only two. Because if you have two periodic orbits which are freely homotopic, the projections to the surface are geodesic, which are freely homotopic. In a hyperbolic surface, you can have only one geodesic, which satisfies that. Okay? So it's 2, the free homotopic classes. Has size 2. So if gamma is closed orbit, let me introduce a notation and I'll use throughout the talk. So the free homotopic class, let me denote that by FH. So here for geodesic flow, the free homotopic class of any orbit has 2 elements. Okay. So we can get 1, we can get 2, and then if we can get 2, the answer to question 2 also yes. We can, using this, we can get finally many. So get covers of example 2, where we unroll the S1 fibers. So this manifold is hyperfibered. Over every point of the surface, you have an S1 worth of directions. So this is hyperfibration. So we can get covers where you unroll the fibers. So then you get a new manifold M1, which is a finite cover of M. And we pull back the flow, we're going to have an Anosov flow in M1. And then in here the free homotopic classes, you can get this so that the size of this is 2n for any n. It's still, all of the orbits are going to have the same, free homotopic classes are going to have the same size, but they can be as big as you want. Yeah? So question 3 is the size in general of this bounded? Well, if it is bounded, then we can always have answer yes to question 2. Or can this be infinite? Okay, which would be sort of, the more you have here, sort of the less likely that that's true. Okay? So it turns out that this is the answer for this is yes. There are some examples I'm going to explain later. But still, the answer to this question is positive. So I'm going to state the result here. And it will all depend on counting how the length of the orbits grows when you have a free homotopic class that's infinite. Okay? So what I'm going to do is I'm going to state the result. Then I'm going to talk about some examples where you have some infinite free homotopic classes, which turn out to actually quite common. And then I'm going to talk about how to analyze the growth of the length in a free homotopic class when that's infinite. Okay? So like I said, we can ask this question for any codimension 1 Anosov flow. We can only answer this question in dimension 3. And you see the methods. Okay? And the number so this is a positive answer to the Handel-Thurston question. And this turns out is actually it's simpler than the next result that I'm going to state, which relates the growth in the conjugacy classes with the topological entropy. So here I'm going to assume that f is the flow is phi is transitive. For example, there's a dense orbit, or the uniperiodic orbit is dense. Franks and Bob Williams were the first ones to produce intransitive examples. So that's a non-trivial hypothesis. Right. Then the growth rate is given by the topological entropy. Okay. And there's also some results about the Bowen-Margulis measure, which is the measure of invariant measure of the flow of maximal entropy, and you can sort of get that as well. All right. So let's see. So let's talk about examples with some free homotopic classes which are infinite. Okay. So here's this is actually old. So we're gonna start with an RR-covered Anosov flow. I'm gonna say what R-cover is in a moment. In a hyperbolic, and there is a small technical condition so that the stable foliation is transversely oriented then for any closed orbit gamma of the flow, the free homotopy class is infinite. So so here's the diametrically opposite to the suspension geodesic flow, that they all have very few free homotopic orbits, really. But here, you know, every orbit is free homotopically many. I'm going to explain why this is true in a moment, because it also introduces a couple of more technical objects that are needed to understand sort of what happens for the growth of the length in the free homotopy class. But before I do that, let me just state that this is a non-vacuous result, that there are such flows and examples. All right, so what is R-covered first? So R-covered means that take the, say, the stable foliation, lift to the universal curver, okay? So the stable foliation is two-dimensional. When you lift to the universal curver, this is going to be a foliation by planes. And R-covered means that this lifted foliation has leaf space, homeomorphic to the reals. Okay? So the two-dimensional foliation in the universal curver. In the manifold, this foliation is actually very sort of complicated globally, because, you know, every stable leaf is dense in the manifold. So when you take the leaf space in the manifold, it's horrible. But in universal curver, it's very nice, essentially because this is a rabless foliation. But this is the condition. Examples. Suspensions, geodesic flows. They are very easy to show that they are covered. Actually, in the beginning, it's a little bit hard to show that something is not R-covered, but there are examples as well. Okay?
So what is leaf space?
What?
What is leaf space?
So the leaf space is the quotient of the universal curve by that foliation. So you take the quotient space here, where, you know, you identify any 2 points which are in a leaf. Okay? So I mean, for the suspension, it's very easy to see. What you get is, you get, you know, the stable and foliations of the torus, and you get the suspension of that. So when you get universal curve, you get universal curve of the torus, which is R2, and you have two linear foliations there, and the leaf space of those is the reals. Okay. Right. So how do you get examples? So examples. Right. So it's sort of easy to get this example. They are not hyperbolic here. So examples of R-covered in hyperbolic. They are obtained by then surgery on suspension Anosov flows. You can get a lot of those. Also then surgery on geodesic flows, and so I did this a long time ago. But also, like I said, Foulon and Hasselblad, they produce some contact Anosov flows. If it's contact, this implies that this is R-covered by a result of Babot. And like I said before, lots of their examples are in hyperbolic 3 manifolds. Okay, so there are lots of examples where you get the condition that the manifold is hyperbolic and it's R-covered. Yes, and the question that is transversely oriented. If you start with something which is transversely oriented and you do then surgery, you're gonna end up with something which is transversely oriented. So if I start with a suspension, so that suspension, the monodromy preserves the transverse orientation to stable, more unstable, you get that. Okay? Now let me explain why you get these infinitely many orbits. All right, so idea. So what I'm going to do is I'm going to start with an orbit, and I'm going to inductively produce other orbits which are fully homotopic to that orbit. And the argument is actually going to be done in universal cover. Okay? All right, so here is a general fact. So this is for any Anosov flow. Here's another leaf space here. This is called the orbit space, which is the quotient of the universal cover by the flow. So here I'm going to identify 2 points which are in the same orbit. This is always homeomorphic to R2. Okay? So topologically, in the universal cover, the flow is a product. Topologically. So geometrically, no, the orbits may be going all over. But this is like R2 cross R. Further, obviously, the two foliations, my two-dimensional foliations, they are saturated by flow lines. So when you collapse them, this induce one-dimensional foliations in my orbit space. I'm going to do certain arguments here in orbit space which are simpler. Actually, it's a device. You know, you could actually do a lot of stuff in the universal cover itself. So I know that the orbit space is R2, and I know that this has leaf space the real. So in this plane, you can think of the stable foliation here as a foliation by horizontal planes, and in the orbit space, horizontal lines. Okay. But what is the whole picture? What is the other foliation? What does it do? So here is a result. So if my flow is R-covered and not topologically conjugate to suspension. So suspension, I'm going to have that every stable leaf intersects every unstable leaf. So it's a total product grid here. Then O has a model. So I'm going to describe what the other foliation is. It turns out that the other foliation, I'm assuming that the same foliations are covered. Turns out that the other foliations also are covered, and it's very simple. So this is going to be an infinite strip where the stable is horizontal segments, as I did here, and the unstable is parallel segments making a constant angle theta, which is not pi over 2 with the horizontal. Okay, so think of this. The orbit space is R2, like, you know, also can get to be this is homomorphic to this. One foliation is horizontal, and the other foliation is going to be like this. Perhaps a clear thing for you to see. Okay. So it turns out, so like I said, in suspension, if you get unstable leaf intersects every stable leaf. This is not the case here. Okay? So I'm going to use this picture and produce lots of closed orbits which are freely homotopic to my closed orbit. This will be the initial orbit. Flow. And this orbit is going to be associated with G in the fundamental group. And let gamma 0 tilde a lift of this orbit, which is invariant by G. Okay? So using this and this picture, I'm going to produce lots of other orbits. So here's my original orbit. So G preserves this orbit, and therefore preserves the stable leaf associated to this orbit, and preserves, more important for us right here, preserves the unstable leaf. I'm going to get all the orbits which are invariant by this G. So where is my unstable leaf? So here's my unstable leaf. Okay. This is unstable leaf. And therefore, it preserves, the G preserves this interval of stable leaves intersected by this fixed unstable leaf. Right. And because the leaf space has leaf space which is homomorphic to the reals. If you have a covering transition which fixes an interval, it fixes the endpoints. So in particular, it fixes the top endpoint. So G leaves invariant this. And if it leaves invariant this, there's going to be an orbit here. So G of L1 is equal to L1. This is the top leaf here. And if that, then G leaves invariant some orbit here. Because if it leaves invariant this, when you project to the manifold, the projection has fundamental group. And it implies that it's an annulus. Okay. The leaves could be in the fundamental group. They are not compact, but they are planes, or at most annuli or maybe bands. With the transverse orientability assumptions here, they have to be annuli. Okay. So there's an orbit here, gamma 1, which is invariant by G. So gamma 1 is contained in L1, and G of gamma 1 tilde is gamma 1 tilde. So therefore, when you project the manifold, this is a closed orbit. And since it's associated with the same G, gamma 0 and gamma 1 are freely homotopic. It turns out actually that the gamma 0 is freely homotopic to the inverse of gamma 1 as oriented orbits. Anyway, we don't need that. And then you can just play the game again and again. Okay? From here, you do the same thing, and you're going to get some L2 and a second orbit here, and so on. Okay? So in this way, we produce infinitely many gamma I, all freely homotopic to gamma 0. Yeah, but I have not used yet that the manifold is hyperbolic. So that's going to come in somewhere, because why are they all distinct? This is because it's hyperbolic. So for geodesic flows, if you play this game, what's going to happen? So you start with an orbit here, the gamma 0. You do this game, and you're going to get the gamma 1, which is the orbit in the same geodesic and traversing the opposite direction. And you do the game again, you go back to the original orbit. So you thought you were getting infinitely many, but in fact it's finitely many. Why infinitely many? So if gamma I is equal to gamma j, notice that these are freely homotopic. So you get the gamma I is freely homotopic to itself, which implies there is a z plus z in the fundamental group of M, and that's why I assume that M is hyperbolic. Okay, so I mean, in this case of geodesic flows, it turns out that you always have two, and that's how you get infinitely many. All right. So, so let's see. So I took longer than what I thought, so I'm not going to explain so much the other examples. I'm just going to mention them. So, okay, so first, still are covered some orbits have infinite free homotopic class, and some orbits have the free homotopic class, which is finite, actually very finite, only 2 elements. So start with geodesic flow. I want to get a big thing here, and I'm going to do then surgery on an orbit which is associated with the geodesic alpha. On orbit from alpha, geodesic, feeling subsurface S1, which is not everything. So this is my S1. So I do something here. I mess up the flow. Here I still sort of have the geodesic flow. Okay. So the orbits which correspond to geodesics, which stay in this part, they haven't changed anything, and they're going to have the finite free homotopic class. Any other orbit which corresponds to a sort of something with geodesic which intersects this alpha here is going to have this property here. Okay. Then there are other examples which are not R-covered. So there are examples which are not R-covered with the same properties as this, meaning some classes are finite, some classes are infinite. So as a matter of fact, the infinite free homotopic classes are very common. So now for this theorem, R-covered is crucial. So suppose I start with an R-covered Anosov flow so that every free homotopic class is finite. Particular example suspension, example geodesic flow, or covers of that. And those are the only ones. So either a suspension or a finite cover of geodesic flow. Sorry if you can unwrap the fiber. So except for these two cases, any other thing which is R-covered is going to have some classes which are infinite. All right, now let me talk about the growth inside an infinite free homotopic class, growth of length. I suppose it is infinite. Let me see, do I have? Right. So let me redraw the picture that I had when I did the proof for the RR-covered thing. So I started with the lift of a periodic orbit, and then I produce this picture here. Here's another periodic orbit. This was gamma 0, gamma 1. So what happens, see, this is sort of the first leaf which is not intersected by this unstable leaf. And it turns out, because you know the topological structure, you have the same thing. So this is what is called a perfect fit, sort of like almost like they are asymptotic. So they don't intersect, but that is very tight. So if I get any other nearby stable leaf, it's going to intersect this, and same thing for the other foliation. Okay? So they don't intersect, but they almost do. And on the other, it actually turns out that there's a perfect fit on the other side. And this whole thing here, which is like a quadrilateral, but there are two sort of ideal points. This is what's called a lozenge. So is a picture where it's sort of like an ideal quadrilateral. Quadrilateral means, you know, in the interior you have the product picture. So this is one of them is stable, one of them is unstable. These are actual corners, these are orbits, and these are sort of ideal corners. Okay? And it turns out that this is very common. Okay? So this is what I needed, the structure for this. So if gamma 0 is freely homotopic, alpha 0 is freely homotopic to alpha 1, corresponding lifts here invariant by G. So G is the covering translation associated to this leaving invariant both of these. So so here I had this picture which I sort of iterated. So what you see here, okay, from this one to this one, here's this object called the lozenge. From gamma 1 to gamma 2, there's a lozenge. So they are connected by this collections or chains of lozenges. This always happens. Okay. So this implies that gamma 0 and gamma 1 are connected by chains of lozenges. So I'm going to start here. So here's one. Here's another one. So these are the ideal ones. These are the actual points. So these are the, I call them adjacent. Here's another one. And eventually I get to the other one. Okay. So there's the sort of the non-adjacent. And then there's the adjacent. The adjacent ones are the ones that I don't like so much. Turns out there's only finitely many. And if I have something which has infinite, sorry, I don't have time to explain this now. I can talk to you later. But turns out if you have an infinite thing like that, so you're going to have this infinite chain, and you're going to have a subchain which does not have this adjacent stuff, only has this non-adjacent stuff. So infinite, so that means that there is an infinite chain of alpha I tilde. So alpha I is in this free homotopic class with no. So the picture is exactly the picture I have there. they're never adjacent. The source keeps to the side. So from one to the next. So I never go to something which is adjacent. Okay. So this will be alpha 1 tilde, alpha 2 tilde, alpha n tilde, and so on. This is called a string of lozenges when I don't have the adjacent jumps. And the alpha I is a string of orbits. So now I'm going to state the result for the growth length of the alpha I in an infinite string of orbits. And then I'm going to talk a little bit about some of the cases. And I will stop. So let alpha I be an infinite string of orbits with alpha 0 the shortest one. Yeah, so for any Anosov flow, the collection of orbits which has length less than any t is always finite. Right? So if you have any collection which is infinite, you can pick, what is the shortest length. That doesn't keep repeating. Okay. Then let's see, what do I want to say here? Then the growth of the length L alpha I, I got the shortest one, is at least, okay, so I want at least because I want the length to grow a lot. The more the length grows, that means that there are less orbits of small length. That means, I have different free homotopic classes. Okay, so that's why I want at least. So first, and it turns out that this result is going to be really associated sort of the dynamics with the topology of the manifold. Okay? So the growth length is exponential in I if m is hyperbolic. Quadratic in I if alpha 0 intersects an atoroidal piece of the Jsj decomposition of M, and 3 linear if alpha 0 goes through consecutive Seifert pieces. Right, and this is all the cases because if not, then it would go just through one Seifert piece. There's only one Seifert piece here. I mean, if it's contained in a Seifert piece, you cannot have the free homotopic class to be infinite. This was sort of part of the previous results. Let me try to give you an idea of why this is true. Okay. Yeah, that will probably be a good time to stop. So the Jsj decomposition, so M gets partitioned in pieces which are either Seifert fibered, meaning there's a foliation by circles, just like in the case of the unitangent bundle, or is atoroidal, which implies in this case for us is hyperbolic. Atoroidal means there's no z2 in that piece. So I'm going to deal with the case 1. Right, so the alpha I is a string of lozenges. So here's, you have the coherent leaves. Say alpha 0 and alpha 1, alpha 2. Okay, so the key thing for us here is that there is a, say, unstable leaf which separates off the stable leaf through alpha 0 and the stable leaf through alpha 1. That's why I need this sort of not adjacent. Okay? So there is unstable leaf separating alpha 0 and alpha 2. This is alpha 2. These foliations, the other foliations have a product picture. So that means that minimum distance between, minimum distance, positive distance between alpha 0 and alpha 2. And that means that, you know, the minimum distance in M tilde between alpha I tilde and alpha j tilde is greater or equal than some global constant times, you know, the distance in the indices. Okay? So as I move here, you know, these things are at least, say, 0.0001 and then so on. Okay? So I have this, and then I'm going to use the hyperbolic geometry to get my results. So, and here's universal cover, which is H3. And all these orbits, they're all associated to the same thing. So they have, all of them have the same ideal point. And this is the geodesic with those ideal points. And because of this separation here, this implies that the distance between alpha I, and let's call this L here, and L, so this is the minimal geodesic with the same ideal points, is greater or equal than A times I minus some constant, which I'm going to call it d alpha 0. Okay? So the bad case is when sort of my alpha 0 is sort of here, and I have to go through, maybe get very close to the minimum geodesic, and then go to the other side. Okay? And this because distances in H3 sort of grow exponentially, meaning if this is a fixed distance d here, and this is r, the length of any path which is at least r, I guess this is not, so this should be sort of like this. The length of any path here which is at least r away from this geodesic is d times hyperbolic cosine of r. Grows exponentially with r, implies that the length of alpha I is at least e to the ai times some constant, which is c times e to the minus d alpha 0. Okay? And that's, so that we get the exponential growth in I here. So let me just say that for this theorem, you know, we get the exponential growth. Now, to get sort of the theorem for entropy, I actually needed an estimate that didn't involve the particular orbit. And for that, you have to work more and get a worse estimate, but that still works. Let me stop here. Thank you so much.